Let's get started. Let me have your attention. Let's get started. I want to welcome you to the University of Tennessee Nuclear Engineering Department Seminar Series, and I appreciate your attendance. These seminars are important, and it's important that we have a good attendance, and we've got that today, so thank you very much. As most of you know, next week is spring break. I'm sure I don't have to remind you of that. So we do not have a seminar planned, but if you are traveling somewhere, please be careful, okay? We want to see you back here after spring break. Today I've asked one of our PhD students to introduce the speaker today. So Dan Stevens is going to introduce the speaker. Dan?
Thank you, Dr. It's an honor and a pleasure to have Dr. Turner here today to speak. Looking over his resume is quite impressive. I hope someday that when I look back at mine, it's equally as impressive. Just a few highlights of many things. A corporate fellow at the Oak Ridge National Laboratory, group leader of the Analytic Dosimetry and Surface Physics Group, graduate of Vanderbilt University, a PhD in physics, adjunct professor here at the University of Tennessee in both the Nuclear Engineering and Department of Physics, a fellow of the American Nuclear Society, the Health Physics Society, etc., etc. And one of the most interesting to me personally, a student of Heisenberg as a Fulbright Fellow, which is very, very interesting and must have been quite a time to spend there with him. So I would like to introduce his talk, which is Studies of Charged Particle Track Structures and Damage to Biomolecules in Aqueous Solutions. Dr. Turner?
Thank you very much, Dan. And Dan called me and invited me here. I was delighted to have the opportunity to visit the University of Tennessee and the Nuclear Engineering Department and my new old friendships and acquaintances. The subject that I'll be talking about, Dan mentioned the title, represents the efforts of a large number of persons out at Oak Ridge National Lab and elsewhere. We will, what we'd like to do is understand in detail the physical and chemical events that accompany the interaction of radiation on matter, particularly matter that is relevant to biological systems. We'd like to know what physical processes occur, with what frequencies, how they develop and go forward in time, and relate ultimately to the production of biological damage. Biological systems are very complicated, and so most of our studies have been confined to aqueous solutions, water with simple biochemical molecules in them. And many cells of the body are 80% water, so there's a lot relevant I think one can learn by this system, which is in many ways very complicated as a physical system, but as a biological system, it's very elementary perhaps. We'll be concerned with carrying out Monte Carlo simulations of the events that take place, and while my background's been in theoretical physics, I'm the first one to say that the arbiter of truth is in what you measure. Something's really true, you go to the laboratory and make the measurements in order to verify things as good as your calculations might be, or as good as you think they might be. So the work I'll be reporting on is a joint effort not only with the calculators like myself, but it involves wet chemistry, biochemists, nucleic acid chemists, and people from other disciplines. And in addition to the people at Oak Ridge, it's a collaborative effort involving Wesley Bolch at the University of Florida, for example, and John McGee and Alok Chatterjee and Warren Garrison at Berkeley. The talk will be divided into the following groups. The scope of the talk I've really just covered. The title again is Studies of Charged Particle Track Structure and Damage to Biomolecules in Aqueous Solutions. I'll review briefly the time frame for radiation events, and then talk in detail about the initial physical and chemical changes within a charged particle track. And I'll show some model calculations of charged particle tracks in water, and then discuss some of the experimental measurements with which we compare our calculated results. And then finally, as a case study in radiation damage, I'll discuss the studies we made of the irradiation of a dimer of glycine. It's probably the simplest amino acid by X-rays. So that's the program to cover these topics. The first thing to look at in the way of the time frame for biological effects, if you imagine acute radiation, such maybe from the exposure at Hiroshima, the amount of the physical interaction of the radiation is over with in a very short time. In regions of a cell, for example, the dimensions of 1/10 of a micron, the radiation has passed through and done its business in a time equal to about 10 to the minus 15 seconds. That happens very fast. And what the radiation does is produce 3 species in water. It produces ionized water molecules, excited water molecules, and secondary electrons. And within that time frame, the secondary electrons slow down very quickly until their energies go below threshold for causing an electronic transition. And for liquid water, we've considered that threshold to be about 7.4 eV. So from an initial blast of radiation in 10 to the minus 15 seconds, you have an array of these 3 species along the path where the charged particle went. Then, with these species suddenly, almost instantaneously produced, there's an unbalance of charge, and the medium right away tries to react, but on a scale of 10 to the minus 15 seconds, that's too fast for chemistry to happen. As a index of time, it takes about a picosecond, about 10 to the minus 12 seconds, a nanosecond, 1,000 nanoseconds. It takes about 10 to the minus 12 seconds for a water molecule to diffuse a distance equal to its own diameter. So the chemistry can't take place on a scale faster than about 10 to the minus 12 seconds. But there is a dielectric relaxation of the initial insult that's put in by the charged particle. And, for example, the ionized water molecule can abstract a hydrogen radical from a neighboring water molecule and form H3O plus, a hydronium atom, and leave an OH radical in its wake. And I'll talk a little bit more about these, but before the chemistry can take place, from a time about 10 to the minus 15 seconds to 10 to the minus 12 seconds, this dielectric relaxation results in replacing these original physics species by species involving free radicals, like the H atom, the OH atom, and the sub-excitation electrons in this time period get thermalized and form the hydrated electrons. Then at about 10 to the minus 12 seconds, these species that are in the track, and on the computer we generate those species in a way I'll talk about in a minute. The identity of each species and the position of each species is known. And then we start the chemistry by allowing these species to undergo a series of steps, random walks, until they bump into each other, so to speak, in which case they can react or they diffuse away. And we follow the progression in time along a charged particle track up to about a microsecond. And at the end of a microsecond, the species have diffused fairly far away, or they have reacted, and there's very little intra-track reaction that goes on after about a microsecond. Now, other stages, biological stages, if you like, in the order of milliseconds, seconds, and minutes, you can have things like cell division affected, and in a matter of hours or days, you can have clinical symptoms appear, and eventually, over a period of years, you may have cataracts and cancer appearing. And these can be related back to the initial set of events. So the chain of events leading to biological effects does start off as a physics problem. From one point of view, it involves a lot of other things. But a good deal is known about the initial physical stages, and that's what I'm going to try to elucidate. That's what we worked on for a number of years. I might point out that 1 year is about 3.15 times 10 to the 7th seconds. So if you take something in terms of years and go back to here, we're talking about 10 to the 22nd orders of magnitude on the time scale of all of these events. Well, I'll show several examples of charged particle tracks that we've calculated. These represent tracks of 3 5-kilovolt electrons in water, and we've done these calculations for liquid water. In each case, the electrons start out going along this axis, or the x-axis, and each of these dots represents one of the chemically active species that is present at about 10 to the minus 11th seconds in these calculations. Now, what we do in the Monte Carlo calculations, we start the electron off in a given direction with a given energy, and in the computer we've logged in the inverse mean free paths for interactions. And the electron can go along a certain flight distance that's determined by the inverse mean free path. Let me point out, where possible, we take the inverse mean free paths or the cross sections and use experimental data wherever available. But the inverse mean free path hasn't been measured for 5 kilovolt electrons. So this is energy as an example of where we've calculated quantum mechanical cross sections to the best of our knowledge in the liquid phase, and we've tried to include collective effects and other things that are of particular relevance to the liquid. But based on the inverse mean free path of the supplied input data, one selects the flight distance for the electron, and the computations moves the electron to the point selected for the flight distance. Then you can choose a type of interaction, be it inelastic scattering, elastic scattering, and among inelastic scattering it can be an excitation or an ionization. And then we pick with a random number a particular fate for that electron at that point. It may be, let's say, an ionization. Given that it's an ionization, we then have an algorithm for choosing the energy loss, the angle of scatter, and the angle for the secondary electron, as well as the energy for the secondary electron. Then we transport the secondary electron and any other secondaries that it produces until all of the energies go below 7.4 electron volts, which is a threshold we'll assume for liquid water. Then we go back to the primary and move it further and so on. And with all of the energy losses, this is a complete track. All of the dots here indicate what this particular electron produced in the Monte Carlo calculation. And this is an example of 3 different tracks. Now, looking back at what's happening on these time scale, one can identify 3 stages of the track development. We have the first stage, which is over with 10 to the minus 15 seconds. That leaves 3 species present: ionized water molecules, excited water molecules, and sub-excitation electrons. Then the second stage is this pre-chemical stage, in which you get a dielectric response within the liquid water. An ionized water molecule, for example, will react with a neighboring neutral water molecule to produce a hydronium ion and an OH radical. The OH is a free radical, that is, it's a species with an unpaired electron. It has an odd number of electrons, and it's something that's chemically very active, as you know. And in later damage, it's these things like the OH radical. For example, it can extract a sugar or an OH from, say, an H or an OH from a sugar on a DNA and cause a strand break. Those are the type of things that we're most interested in. This is a star. H2O star is a excited water molecule. Some of the energy can be transferred from the primary electron into vibrational excitations, for example, of the water molecule. Without ionizing it, it transfers energy. And with the excited energy, the water molecule can dissociate into an H plus an OH. Now here you have 2 free radicals produced in that reaction. And it can also auto-ionize, going back to an H2O plus and a free electron. The secondary electrons that are produced up here, these are slowed down to sub-excitation energies in this first phase. They become hydrated over the time period of going up to about 10 to the minus 12 seconds. Now, the electron is negatively charged, and the water molecule has a strong permanent dipole moment. So in this time, the electrons become thermalized and become hydrated. They align themselves with the dipole structure of the water molecule. So then your original track originally was an array of these 3 species, is now an array of a number of other species involving free radicals. And When the time has come to 10 to the minus 12 seconds approximately, then that's time enough for the chemistry to begin. And 10 to the minus 12 seconds, I mentioned, was about the time it takes a water molecule to diffuse a distance equal to its own diameter. So in the track, wherever we have these free radicals and other things that have been formed, they exist. So we have an array. What we do to simulate the passage of time starting at 10 to the minus 12 seconds is to consider a time typically of about 3 picoseconds. Imagine that the time of 3 picoseconds elapses now starting at 10 to the minus 12 seconds. In 3 picoseconds, we take each of these species, the computer knows which it is, and imagines that it diffuses randomly. In 3 picoseconds, the time is so short that this will not jump a large distance compared to its own size. And we jump each of these species randomly by a distance selected from a distribution that depends on the diffusion constant for that particular species. And so we jump each of these once in a random direction, and then we go back in the code and see if 2 of these jump close to each other. If they jump close to each other, we can consider that they had a chance to react. And each of them is assigned, or each pair is assigned, a reaction radius, and the reaction radius is based on the rate constant for the particular reaction. For example, you might have an OH here, and an OH here, and after they all jump, we go back and see if 2 of these are overlapping, and maybe these 2 jump into each other. We would say then that the OH and the OH have combined form H2O2, and we would remove that from a track and can score that as one particular product that was formed. So we jump them all and look at all pairs to see which overlap, clean out any which have overlapped, and that's what we use to simulate a reaction between the pairs. Then we take the remaining ones in the track and jump them again randomly, go back and look at all pairs, cause some reactions, and then we keep jumping those and progress in time in that fashion. The chemical reactions are considered here, for example, OH plus OH, H2O2 that I mentioned, and I won't bother to read these others, but some of these combine, most of them combine to form products like H2O, H2O minus, or H2. This particular reaction with a hydronium ion and a hydrated electron produces an H radical, and that goes back in as a reactant. And there are other reactions that can occur, which I haven't listed here. And also we've carried out calculations for the presence of oxygen, dissolved oxygen in the water. The calculations I'll report on today are all without oxygen present. So let's look in a little more detail at a particular track. I think it'll give you a better feeling for what we're trying to do. Okay, this is another example of a 5 kilovolt electron, like I showed you a couple of times ago, with dots being the species formed at early times. And these ticks, which I guess you can hardly see, but this is a distance of 1,000 angstroms to give you an idea of the scale that we're on. And what I've done here is come to the early part of the track and blown this up 20 times and looked at the beginning of the track on a larger scale here. So this is a blown up view of what's happening right here. And this shows the species at 10 to the minus 15 seconds. So the initial electron is just shot out from the origin going horizontally, and it's done all of this within the first 10 to the minus 15 seconds. The species shown are the ionized water molecules by these triangles, and the circles represent the excited water molecules, and they're also subexcitation electrons, which are not shown here. But the electrons started off this way and produced these clusters of initial events, the excited water molecules and the ionized water molecules. Now you can see some of the clustering, which is known for a very long time and recognized in radiation chemistry. When you have a secondary electron produced, for example, it's liable to produce maybe 1 or 2 more ionizations. So if you get one event, you're actually have a high probability of getting a group of events or a group of reactants. And then in the dielectric relaxation stage, third stage, these events now have been transformed from the ionized and excited water molecules into the group of reactants that involve free radicals. For example, here was an excited water molecule in this particular calculation at 10 to the minus 15 seconds, and then at 10 to the minus 12 seconds after the relaxation, that is dissociated into an H and an OH. And in the middle is a hydrated electron. Evidently, this excitation was produced by the last gasp of the electron. It was the last event it had before its energy dropped below threshold. And then you have the group here of the hydrated electron, the OH radical, and the H radical. Then we start the chemistry here, and we imagine the passage of 3 picoseconds. Each of these is jumped, and look for species that overlap and can react. And then everything that's left jumped again, and that's repeated, and so on, to carry out the evolution of the track in time. And the next view graph shows an example of a complete history of the track. Again, a 5 kilovolt electron stops off here, and the time sequence goes down. This particular electron produced 1,174 species at 10 to the minus 11 seconds, and then jumping in time carries us on down to later times. You can see here the track keeps its structure about 10 to the minus 10 seconds, and then begins to span out visibly. And we've carried this forward to 2.8 times 10 to the minus 7 seconds, and there are a total now of 410 reactants left from an original number approaching 1,200. At this point, the remaining species are so far away that there's little likelihood that they will continue reactions. Mostly, they just diffuse away. Now, looking back, we started these calculations in the 1970s, and they were done on the mainframe computers out at ORNL, and how times have changed. At any given time with these Monte Carlo calculations, I'm sure many of you are very familiar with it, we've used the capacity of any computer available. If you look at this particular calculation, for example, which is just 5 kilovolt electron, here we start with this an array of species, over 1,000 species, and we want to jump each of those 1,000 species, pick a random direction and jump them. Then we want to go back and look at each pair to see if any pairs are close enough together to interact with one another. So with 1,000 species, 10 to the third species, you have about 1/2 times 10 to the 6th pairs to look at. And then you jump all of these and look at the pairs, and then you clear the ones out that have reacted. And then you jump them again, and each jump corresponds to a passage of about 3 picoseconds. If you make the jump time longer, then you have the possibility that 2 species would jump through each other and might not react. So we keep the jump distance small. And if we go from 10 to the minus 11 seconds to 10 to the 7th, you're talking about a span of 10 to the 4th or 10 to the 5th in time, and you have 10 to the 6th pairs. So you're talking like 10 to the 11th operations just for a 5 kilovolt electron and for one track. And for doing calculations like this, if you're doing those calculations or you want to simulate the frequency of strand breaks or something like that, then you need to study many tracks and get good statistics. So really, at any given time, we had filled the capacity of the computing capabilities. And going back to the 70s when we started doing this work, we were using the IBM mainframes out at the lab, and we would run at night because things were cheaper at night. And well, I think one of the biggest changes I've seen has been the storage. Storage was such a premium. You'd have a doubly dimensional array, and you'd dimension it maybe 100 or something like that. And as the computing capabilities progressed, we could run more cases. We could use higher dimensions, more memory. We didn't have to use tapes, and we didn't even have to run at night all the time. We could go out during the day when things were more premium. but we were really just at the limit all the time of what the computing capability was. Now, right now, I run these on my PC at home. I have a 3.5-year-old PC with a Pentium chip, and I run these at home, and they go very fast. And just recently, one of the arrays I had historically that was dimensioned at 120, and things were really being pushed. We had print messages in there. If this array ran over, then stop and print out what had happened and so on. Well, this one set of arrays, I think there were 6 variables like that were dimensioned. I just dimensioned each of them 20,000. Compiled and ran. Didn't have to worry about exceeding 120. That's been the biggest change. Of course, doing these on the PC is a lot more convenient than having to go with the mainframe. So basically, that's how we do the calculations, and I'd like to discuss some model calculations next. As I mentioned, my background's in theoretical physics, but I think what you measure in the laboratory is the arbiter for truth, and I want to show you here a couple of real tracks. These are autoradiographs of alpha particle tracks from americium-241, and this is a track from carbon-14. These are biological experiments that we done. And so, in some vague way, if one's being charitable, that does look kind of like the tracks we're calculating, or at least we think we have a reasonable first approximation to what's going on. What we're really trying to do is have the reactive species on the computer do the same thing as they do in nature, at least on a statistical basis. And as I mentioned, our data input is experimental data wherever possible, and otherwise we've worked out theory, and we've also made a large number of experimental checks on our work. And we're in a position, let's say, is our code right? Are we correct? I think that's not as valid a question as saying what we're doing when we compare our results with the experiment is providing a necessary but not sufficient condition. That is, it's necessary that everything we calculate that can be measured experimentally, that there's agreement, but that doesn't really validate the code. It's a necessary but sufficient condition for us being correct. I'll give 2 examples, and that just indicate I'm covering a lot of material, but maybe give you some of the flavor for things that we think we can be learning. This is an example of a electron track going vertically into the plane of the drawing at a distance of 50 angstroms from a double helical array of dots which represent the location of alternating sugars and bases on our DNA chain. So this is a 20 angstrom diameter chain, and the spacing of those are what's on the DNA molecule. The electron track is going straight into the page. One thing we can do in the computer that we can't do with nature is to make that electron go straight. So we just made it go straight for this particular example. It illustrates several things. This is the early event. The dots are out here in the water, and some of the dots are within the helical structure of the DNA, or at least they project it so, but you can make them so. So in principle, one can distinguish between what's called the direct action of radiation on biological molecules and the indirect action. The direct action would be the passing electron can cause a quantum transition in the DNA itself, or generally in a biological molecule itself. The radiation can act directly on that molecule. The indirect action of radiation is exemplified by a radical that's produced in the water, and that radical diffuses over toward the DNA and then does its damage when, like, for example, a strand break that it can cause. Now, in this particular calculation, we didn't use pure water. We simulated a scavenger in the water that's about the strength that we think would be characteristic of a cell. So, under conditions, idealized conditions for cellular, what we have in a cell, these radicals are interacting with themselves. They're also diffusing, and some of them are reaching the DNA that we can score then as damage to the DNA. But now there's a competition for those radicals to live long enough because they can be scavenged by the rich chemical environment of the cell. And in about 10 to the minus 8 seconds, radicals that haven't interacted with themselves or with the target molecule, have been scavenged and don't exist. And I think that argues strongly that the interaction of radiation on a molecule like DNA in a cell is localized to within the distance that a radical can live and diffuse, and that's about 20 angstroms, maybe 30 angstroms at the most. So the radiation has to pretty well hit the molecule to within about 20 or 30 angstroms in order to damage it. Otherwise, that's the extent of isolation in the basic physics of what's taking place, we think. Another example is afforded by a track segment of a proton going by DNA, an array that simulates DNA very crudely. Proton is going across. These dots again represent the sites of active species at 10 to the minus 12 seconds. And here's the double helical array, roughly simulating the positions of bases and sugars in DNA. Now, the scale here is 5 nanometers, and this is a 1 MeV proton, which is not a particularly high LET proton. Doesn't have a very high linear energy transfer, say compared with an alpha particle or a less energetic proton. But compared with what one saw with the electron, where we had a scale of 1,000 angstroms being shown, this 5 nanometers, one has many dots within dimensions comparable to the structure of DNA, which means that compared with electrons, the protons are giving multiple hits, or can give multiple hits within a DNA, and there should be a greater propensity for, let's say, double-strand damage from this high LET radiation compared with electrons. That's not news to anybody, but the computations enable one to deal somewhat quantitatively with that, and probably, hopefully, with reasonable estimates. Well, another thing I had on the outline was that we wanted to keep the calculators honest and make experimental comparisons where possible, and we've made many, many experimental measurements with our calculations in the work. As I say, this is a necessary but not sufficient condition to show that what we're doing is correct. But here's an example of one such study where plotted the yield of carbon dioxide from irradiation of formic acid solutions. What's plotted here is the G value for carbon dioxide that's produced. This is a aqueous solution of formic acid irradiated by energetic electrons in the MeV range. The G value of the yield, that's the number of carbon dioxide molecules produced per 100 eV of energy absorbed. That's plotted against the formic acid concentration in molar, going from 10 to the minus 4th molar up to 1 molar, slightly beyond. Now, the experimental measurements are shown by these boxes. These are the data that's gotten. And the analysis of Laverne and Pimblott at the University of Notre Dame is shown by these open circles, which is the upper line. And our simulation is shown by the closed circles, which is the lower solid line. So we have a good general agreement between the boxes, which is experimental measurements, the Laverne and Pimblott analysis at Notre Dame, which is the upper line, and our own code gives this for the yield as a function of energy for carbon dioxide production from formic acid solution. We've done studies also with bromides and nitrides, methyl chlorides, a whole bunch of other compounds in aqueous solution. We've also done studies of the time-dependent yields of some of the products. For example, the hydrated electron with pulse radiolysis experiments, the hydrated electrons are produced, and then the number of electrons, relative number of the hydrated electrons as a function of time can be read experimentally. So the time-dependent yields of hydrated electrons from radiation with high energy electrons has been measured experimentally, and we've made our code go right on to reproduce that data. In fact, that data is used to adjust things like the thermalization distance for our electrons and many things that go into the code. We have to have a code that gives us the measured data for the hydrated electrons. On the other hand, having that data provides us with limits to so-called adjustable parameters within the code. And so that's one example of experimental data that's gone in directly. The time-dependent yields of the OH radical has been measured, the relative yields, and we fit those also, and other things. So we've tried to give a lot of attention to experimental checks. And the last topic is really, well, we've tried to put all of this together to do a case study. We selected a biological system, a biological molecule that would enable us to, for which there was pretty good experimental data already, and for which we could apply our code. And we looked at oligonucleotides, DNA pieces, things like that. These are all quite complicated. And what we decided on is to do a study with a polymer. And the simplest amino acid is glycine, the residue is CH2, and a dimer of glycine, which is two CH2s put together. I think that's about as simple a biological molecule as one can have that shows some relevance. It's a dimer of glycine. And it turns out that from one point of view that choosing that was the easiest system. Also, experimental data, good experimental data existed on that. In the 1970s, Warren Garrison at Berkeley had suggested the chemical pathways by which gamma rays lead to damage and measurable products from glycoglycine. So we chose that. This was sort of this at least was a thesis that Wesley Bolch did here at the lab years back. And the dimer of glycine is called glycoglycine. The residue is CH2. These are the two, and this is the peptide bond. So if you cut this much out from here over to here, slice all of that out, and what you'd have would be one molecule of glycine, the simplest amino acid. So this is two of those. I mentioned this was a simple system to study biologically, but it was a complicated one for our uses. And one of the troubles I had with this system was learning how to spell it. I couldn't spell glycoglycine, so I still have to stop and think about it. But we chose to do this. Now, the first three products that I mentioned that are formed by radiation in water were hydrated electrons, OH, and H radicals, among other things. The glycoglycine molecule at the concentrations we were looking at is so small that when you irradiate a solution of it, almost all of the interactions occur in the water itself. You have an occasional interaction with the molecule, the glycoglycine molecule itself. So it's a good approximation, except if you don't go to very high concentrations, meaning above about a mole, then we can consider all of the action of radiation to be indirect. The radiation produces its things in water, and then that interacts with the dissolved glycoglycine. The hydrated electron and the OH radical and the H radical are the three things that attack this molecule. And as Garrison had postulated back in the 70s, the hydrated electron comes in and forms a electron adjunct with this molecule. This is a soda, and it's neutral, but its charge is separated. And the hydrated electron results in this CN being broken off here and forming free ammonia, and it leaves a radical here which we call the deamination radical. So the hydrated electron breaks this, giving you free ammonia and a peptide radical which is called the deamination radical. The H and the OH radicals that are produced in the water abstract the hydrogen mainly from this end. So an OH will migrate out and take this off, and that leaves a hydrogen abstraction radical. That leaves another peptide radical which is free to move around. And I'll give you a sample of the subsequent chemistry that Garrison had postulated and we built into our models. Don't try this as awful. Don't worry about the details of this, but just let me indicate the kinds of things, the kinds of reactions that we had to consider in detail. The OH and H I'll give you the hydrogen abstraction radicals to start with, and the hydrogen electron gives you free ammonia and a deamination radical. Now you've got these peptide radicals that are present, and the diffusion constants for those were only known incompletely, and also the rate constants for those reactions were known only incompletely, so we had to assume rate constants for those reactions. For example, the hydrogen abstraction radicals, two of those can combine to form a precursor for diaminosuccinic acid, which is one of the products that's being measured. And one has a whole series of reactions, and you have chains of feedback in here. For example, the deamination radicals that are produced here, they react with the glycoglycine that's present and form hydrogen abstraction radicals, which are produced also directly by the radiation, and the hydrogen abstraction radicals can feed back in. So for something like the diaminosuccinic acid precursor, you get two sources for that product to be formed, and we had to fit all of these things. And this represents some of the results that we had. This shows the concentration of the various reactants as a function of time, starting back at very early times when the radiation was turned on. This was done at 2.8 gray per minute X-irradiation with 250 kbp X-rays. We used the X-ray spectrum, the dose rate, and everything that was in the experiment where we were measuring these products, and used those conditions in the calculations. The products that were measured I mentioned the diaminosuccinic acid, for example. These, of course, none of these are present when you start with, and at later times, at about 1 second or 100th of a second, the diaminosuccinic acid builds up, and then it takes an increase. This shows the concentration in the solution plotted as a function of time. This shows an increase, and this increase starts where you get that other mode of production that I mentioned from the hydrogen abstraction radical. At early times, the diaminosuccinic acid is being produced only in the single tracks of secondary electrons produced by the X-rays, intra-track reaction. And the pictures I showed where the products had diffused out and weren't reacting anymore within the individual tracks, those leftover radicals were used as source terms. When we went to these later energies, later times, we carried out those computations by differential equations, ordinary rate equations that one has in chemistry. And this shows where that second process began to kick in, and until that radical came to equilibrium. Then you had the diaminosuccinic acid produced at a higher rate due to the addition not only of intra-track reactions, but inter-track, where you've got the overlap of different tracks. All of these details, everything comes out in wonderful detail in the Monte Carlo calculations. That's a nice thing about it. For example, we can answer questions like, for example, the aspartic acid that we were measuring at 5/100th of a molar concentration, 93% of that was being produced by track overlap. When the concentration was raised to 1.2 molar, then only about 10% were produced by track overlap. The other things were being produced at high concentrations within individual tracks. And all of the ammonia was produced in individual tracks, even at high concentrations, because that was so fast. Well, let me summarize what we've been talking about. The plan has been to try to account in microscopic detail for what radiation does to this molecule. And I think we've been successful in accounting for the measured rates. Microscopic events all fit together, and I think there's a hope that the computations wouldn't be right for the wrong reasons. That is, things must be happening roughly like what we're saying, if not better than roughly. So we've used experimental data where are available. And the studies now have moved to the University of Florida, largely conducted by Wesley Bolch. And Bulent Eidogan, do you remember him? He was here, got his master's a few years ago here at the Nuclear Engineering Department here at UT. He's finishing his PhD with Bolch at the University of Florida now. and I'm on his PhD committee. He'll have his defense next month. But work is going on like this in Japan, in Germany, England, and France. But the program here that was long-term supported under the Department of Energy was closed down about 6 or 7 years ago. There's virtually no effort going on now like this. At least not. Physical sciences have some work going on in radiolysis of water, but not the biomedical program that we had earlier. So let me thank you for your attention and say that it's been a pleasure to be here. Thanks very much.
Okay, we have time for a few questions or comments.
Okay, Dan. Have these models been extended to heavier charge particles? You mentioned protons and electrons specifically. Has this been extended to systems where you have heavier charge particles as the incident radiation?
Yes, we worked quite a bit on alpha particles and formic acid. And what we're running into problems with, I think there's a lot more work that needs to be done. One thing we suspected was the alpha particles produced with such a high density of ionization that we have to take into account electrostatic effects between the charged species that are produced, which we haven't done with these tracks. Now that is probably true, but we haven't done that. And then, of course, the cross-section for electronic transitions for very slow alpha particles is another ballgame. That's how those things aren't known experimentally. And calculations with the slow ions are difficult. It's sort of a yes and no. We've worked some on it, but haven't got it. Larry?
What are the physical sizes of these tracks, say, for alpha particles? Are they, micron in diameter? What is the shape? If you could draw a shape of, would it be a teardrop? It only goes a few microns. Relative length and diameter, if you were to draw a perspective, what dimensions would you put on it?
Say something like this.
That's exactly what it would look like?
Yeah.
For an alpha particle?
Yeah.
Wouldn't it be peaked at the end, or do Brad peak?
Well, if you're plotting the number of, if you're darker, if you're plotting dots for each ionization or excitation, then of course they're more in the Bragg peak. But the track is, probably tens of angstroms wide, and maybe 70 microns in unit density material, or less than that, 50 microns.
But it's only 2 microns in diameter.
Well,
2 angstroms, you said.
Yeah, we've done some calculations. Occasionally you get a high energy delta ray from an alpha particle, and in that case the track was like this, and occasionally the delta ray comes out quite far, but those are very rare events, but they're energetically possible, and the probability is not zero.
In the Notre Dame simulation, there was a small, this was the G for CO2, I think you showed?
Yes, that's what I showed.
There's a small difference. This is not statistical. They must have used different cross-sections.
They did an analysis using inverse Laplace transform, where you have the time-dependent concentration, and then the e to the minus st is the pseudo first-order reaction probability, or the survival probability. Then you invert that transform. So they didn't they have done Monte Carlo, but that particular analysis is analytic. But you don't know the transform, so they're making assumptions about that, the inverse transform.
Kathy, you had a question?
Yes. Do the charged particle tracks change the local polarizability of the medium surrounding the biological molecule?
The polarizability of it?
Yes.
Yes.
So does that alter the stability of the molecule?
Well, I'm not certain I understand everything you're asking, but for example, the water molecules orient themselves around the thermalized electron, for example, and that definitely changes things from what they were before.
So, for instance, could that reduce the charges between the phosphate molecule and or
Yeah, it neutralizes it, yeah. And the studies I mentioned at the University of Florida, which are on DNA, they consider a hydration layer around the backbone of the DNA, not the water molecules, which have some rigidity, some permanency.
Okay, I have a question. I guess you could call it a department head's question. Since DOE is not funding work like this anymore at Oak Ridge, but Wesley Bolch and his student are funded, where do they get their funding from?
Okay, the program was not just closed out at Oak Ridge, it was closed out nationally. It was budget category. And our counterparts at Hanford and Berkeley and other places, and university contracts with those, that category of funding was zeroed out. That connection went down to the genome. Bulge has gotten some university professors of some health physics kinds of fellowships on a very limited basis, enable them to keep on, and some private funding there, as I understand it.
Okay.
But he's an great thing like everybody else.
Yeah, sure, I understand. Any other questions or comments? All right, let's express our appreciation again to Jim. I remind you that we do have refreshments down on the second floor, and everyone is invited.